Welcome back. In this video we'll talk about the finite horizon optimal control problem, finite horizon linear quadratic optimal control problem. And here is a non-technical problem description. So we have a dynamical system, xt plus 1 is a xt plus b ut. Now look, for generality, actually a can depend on time t and b can depend on time t. That doesn't make the problem more difficult. Assume that at time 0 we are at a given and known state x, and we want to find a way to steer the system state towards the origin. So the problem more or less is stated as: find a finite sequence of control actions, find the u0, u1, u2, u3, so as to move the system state from x0 to x1, x2, x3, and finally x4. This is a problem with horizon n equals 4. There are many ways, of course, to go from this point close to the origin and even closer, perhaps. Maybe a way to go closer would be that. But it doesn't mean necessarily that this second trajectory is better than the first one. Why? Because, for example, that second trajectory might be very costly in terms of control actions. Maybe, so to speak, you need to consume a lot more fuel to drive your system like that instead of less aggressively this way. So now what we're looking at actually is a way to quantify how good these trajectories are. And this is called the cost function. The cost function is given by a function of the control actions, u0 up to u, whatever it is, n minus 1. So you see here we have n equals 4, goes up to u3. And of course the cost function depends on the initial state. And one possible way to construct such a cost function is to go through all states, go through all times, from time 0 to n minus 1, and penalize the distance of the state at that time t from the origin, but also the distance of ut from the origin. And one way to do that is the following. We will just put a small 1/2 here for reasons that will become clear later. And at the end of the horizon, if you do that, you will have penalized x0, u0, x1, u1, x2, u2, x3, u3, x4 is missing, so we need to penalize that separately. How far is that from the origin? And that will be xn transpose a matrix pf xn. Now what are these matrices q, r, and pf? By the way, q and r are allowed to depend on t, if that is relevant for your application. These matrices q, t, and r, t, and pf are symmetric. All of them are symmetric. Q must be semi-definite. RT must be positive definite, and PF must be positive definite again. In case you don't remember what it means for QT to be positive semi-definite, it means that for all x, for any x in Rn, this is non-negative. And what it means for R to be positive definite, it means the following. So a positive definite matrix is a positive semi-definite matrix with this additional property. If U transpose RU is equal to 0, then U must be 0. In all other cases, it means that if U is not 0, This must be strictly positive. Now, we don't have to write symmetric positive semi-definite every time. We can use this very simple notation. Sn plus for positive semi-definite. S dimension plus plus for positive definite. So once again, we need to steer the system state from an initial state to as close as possible to the origin. All of these states must be as close as possible to the origin, and all these inputs must be as close as possible to the origin. And we measure this proximity using this cost function that quantifies and it gives a measure of the distance of all these states from the origin. And we have introduced here some matrices Q, R, and PF, which are called weight matrices or weighting matrices. Now a few comments about these. If you take Qt, for example, and you take the simplest possible case, Qt equals the identity matrix dimension n, then X transpose QTX. Okay, I'm dropping the indices here for simplicity. You can have them if you like. This is nothing but xt transpose xt, which is the squared norm, right? And what is the squared norm? It is xt if xt has components 1, 2, 3, and so on. What is this sum of squares? Now, if I don't want to use qt equals I, if instead I want to give more importance to xt1, to the first component, let's say for some reason it is very important. If I want to give a higher gravity to that element over here, I can multiply it by a certain number, x100. Now this will be precisely, xt. This can be precisely written in this form, xt transpose qt xt, by choosing qt simply to be equal to that. And you can modify all other coefficients here. For example, if you want to put a 5 over here, then the last element must be a 5 and so on. So if you, then often we do that in practice, we can select Q and R to be diagonal matrices, and the meaning of these diagonal entries are that these are weights for the corresponding elements in a modified norm, a weighted squared norm actually. So the problem now becomes minimize this function. Minimize this function, but take into account that we have a certain system dynamics over here. It's time to write down the problem in a proper mathematical way. So this is the problem we want to solve, minimize this function subject to these constraints. And it would be a lot simpler if the problem were given in this form actually. If we were able to write the problem in such a way, minimize some function f without this peculiar subject to, then it would be very easy to solve it, especially given that function f is convex. Now, why is that? I'll leave it up to you to confirm that the cost function we have in this case is indeed convex. But since f is convex and it is also smooth, meaning in this case we mean differentiable, solve this equation. Solve this equation, and if you find the x star that satisfies this condition, then x star is a minimizer. X star is a global minimizer. But unfortunately, this is not an unconstrained problem. This problem here doesn't have constraints. It's called unconstrained. This is a constrained problem. So these conditions must be satisfied. I have some very good news for you. We can somehow, very easily actually, get rid of these equations over here. How? But simply by writing out these equations from time 0 to time n-1. So let's start. x0 is x. What is x1? I'm just copying this equation for t equals 0. And I will write it again for t equals 1. The objective now is to get rid of all these xt's, so to have nothing in the constraints. The first equation is absolutely fine because it is just a constant x. The second equation involves x0, but we can plug in x0 from the previous one and we can have, so that's fine now. The next equation has x1 in it. We want to get rid of it. How? But we can, that's a no-brainer. Just take that, plug it inside here. Take x1, plug it inside there, and you will have, okay, simplify it a little if you like. And keep doing that. Let's do it once more. So you might be able to see a little pattern over here, and this allows us now to get rid of all these states x. So what is the, let's denote x boldface, let's say x underline actually to be more clear on paper. We can now get rid of all these states. We can eliminate them using the equations on the right hand side. So x0, we know, let's write them just one below the other. x0 is x, x1 is that, and so on and so forth. What we'll do right now, let me draw a line here. What we'll do right now is that we will denote the decision variable we want to have, and this is u underlined, and this is just u0, u1, down to un-1. And we'll make a very important observation, that this x underlined is given by some matrix A calligraphic times the initial condition x plus some other matrix B calligraphic times the sequence of control actions u. And what is this A calligraphic? Note here we have identity A0, A1, A0, A2, A1, A0, and so on. So this matrix A calligraphic is simply, and then as we go down it will be a n-1, a n-2, a1, a0. So this is matrix A calligraphic. What is matrix B calligraphic? So this is now simply 0. The first one doesn't depend on u0 or u1 or u2 and so on. The first one, we have a b0 here. b0 times u0. Next we have the third one now is the following. I'm copying these values from this equation. So a2, a1, b0 multiplies u0, this multiplies u1, and this multiplies u2, b2 times u2, b2, u2, and just continue and fill in the whole matrix. So I'm saying this again. The sequence of all states, x0, x1 down to xn, depends on the initial state x and the sequence of all control actions. And the dependence is explained by this equation. Now, what this says about the problem is that we can actually get rid of the state sequence. And let's see how we can do that. I'll keep it here on the side for you to see. Let me fold it. I'll keep it here on the side, but that's all we need. That's the only equation we need. So I'll write it here again. The sequence of states is A calligraphic times initial state plus B calligraphic times sequence of control actions. What is the cost function? This is the cost function, right? But if you look closely, this is a function of u0, u1, and so on. On the right hand side, we have some unwanted variables, and these are all these xt's as well as xn. These are unwanted. But we know what x0 is equal to. It is equal to x. We know what x1 is equal to. It is equal to a0x plus b0u, and we know what all the x's are equal to in terms of these variables that are fine. They are welcome. Xt are unwanted, ut and x are just fine. So the first thing we'll do here is we'll move 1/2 outside. As far as the first term is concerned, we'll write it like that. And here we will write all the q's. Qn minus 1, and the last one will be pf. Don't forget about this one. We don't need this paper anymore. Transpose here. So this function can be written compactly in matrix notation like that. Now this is x underlined, and this is just u underlined. Let's give this matrix a name. Let's call it Q underlined. I don't know. Let's call it Q bar. And let's give this other matrix another name. Let's call it R bar. So overall, we will have written this cost function very, very compactly like that. 1/2 x transpose Q bar x plus 1/2 U underlined transpose R bar U. And that's brilliant now, because this definition allows us to write the original problem in this form. So minimize subject to, over U underlined function v of U underlined and x. But what is x underlined? Isn't it ax plus bu underlined? So now this way we have written the cost function without unwanted variables. So without x underlined, there is no x underlined in there. What we have is just u underlined and x, which are absolutely fine. We have written the function really, we have written the problem really in this form: minimize a function of u underlined and x. And the solution to that will be gradient of v equals 0. So we will be looking for a u underlined star, the best u that solves this equation. But okay, let's not get ahead of ourselves. This function v, I'll write it again once again. Let's do the algebra and simplify things. Q. So this is what we have: 1/2 x transpose a transpose q bar ax. This term, this first term, is just constant. X is constant, everything else is constant, doesn't depend on u. This is a quadratic term, u transpose times something times some quantity times u. So this is linear in u, this is quadratic in u, and this is the function we want to minimize. This is the function we want to minimize with respect to u bar. I missed a bar here, sorry, underlined. Now, as we said, this term is constant and it contributes nothing to the optimization problem. So in fact, why don't we get rid of that? We can really remove it. If you're not looking for the optimal value of the problem, if you're just looking for the best u underlined, then you can simply ignore this term. It's like you have the problem minimize f of z and minimize f of z plus 1. Or it's like you have this function and you have this function, which is the same plus 1. The minimizer z star will be exactly the same. So we can get rid of that. And this is the function now. What is the gradient of this function? Sorry, here I wrote u bar, it should have been u underlined, is the correct notation. So what is that? That must be equal to 0, right? To find the best, the optimal u underlined. But what is the gradient? Here we have a quadratic form, so it is 2 times with 1/2, it goes away. This is a symmetric matrix. Let me remind you that actually. This is very useful. We will be using that all the time. If A is a symmetric matrix, this is equal to 2AZ. 2 with 1/2, the 2's get eliminated. So that plus, and another thing to remember, when you have the gradient of an inner product C transpose times Z, this is equal to C. So what is that? This is equal to, well, if we must, we have to write it down properly. To see clearly the transpose over here. So this is it, and this must be equal to 0. Now it's not difficult to move that on the right hand side. Now I know what you want to do. You want to solve for u to find the optimal value and solve the problem, but pause for a moment and think. I mean, you want to write that. You want to write that -1 The question is, are we allowed to take the inverse of this matrix? Is that matrix invertible at all? The answer thankfully is positive. Why is that? Because R bar, you remember by definition it is R0, R1 down to Rn minus 1, and all these matrices Rt are positive definite, so this whole thing is positive definite. So that's one thing. Second, this form here is positive semi-definite. Positive semi-definite plus positive definite is positive definite, meaning it's non-singular, meaning this is absolutely fine. There is no problem with that. What have we achieved here? We have solved for u star, that's the best u, and we have determined the best sequence of control actions. So the best sequence of control actions, to be very clear, the best first control action, the best second control action, the best n-1 control action is equal to some matrix, this matrix. Let's give it a name. Let's call it Kn, where n is for the horizon of the problem. So Kn times x. Let me give you an overview of how we solved the problem. So again, the original problem was to drive the system state from x0 to as close as possible to the origin, and we penalized the distance of all these states and control actions from 0. In fact, we introduced this cost function, which is the sum of stage costs from 0 to n-1, plus, of course, we shouldn't leave out the terminal state. And all these cost functions we used are quadratic. So we did that, and then we said, okay, if we had no constraints, if we had an unconstrained problem, we would simply take the gradient, set it equal to 0, and solve the problem. But it's not the case. We have some constraints. Let's eliminate them. By eliminating, we mean solve for x0, x1, x2, and so on, and express all these variables in terms of u0, u1, up to un-1. And we did that. We wrote each one down carefully, x0, x1, x2, and so on. And x1, for example, was a0, x plus b0, u0. x2 was this expression that you can see it depends only on this constant, u0, u1. This depends only on the constant. The initial condition depends on u0, on u1, and u2. So all these are absolutely fine. After that, we went here. We introduced some more compact notation, x0, x1 down to xn, and for u, we introduced the notation u underlined u0, u1 down to un-1, and we were able to write the whole system dynamics from time 0 to time n-1 in this nice form. Now that we did that, the next step was to try to get rid of these unwanted variables. So we organized the variables in x underlined and u underlined. We wrote the cost function, the total cost, we wrote it down like that, and it's good here that we have x underlined showing up, because we can replace x underlined by this expression. And here. We did a little bit of algebra to write this cost function v in terms of x u underlined in this form, which is quadratic. This is a quadratic function. We wrote again here the problem, minimize the cost function, no constraints. Now there are no constraints. We got rid of the constant term and we said, okay, what do we have? An unconstrained problem. It is a smooth function, it is a convex function. How do we solve it? Take the gradient of the cost, set it equal to 0. Equivalently, we took the gradient of the quadratic function, we solved for u star, and this is the solution. And u star underlined, meaning all the control actions, u0 star, u1 star, and so on, are given by some matrix that we can compute just once, and it's actually nothing complicated here. We just have to solve a linear system. We have to multiply by the inverse of a matrix. Let me say here, in practice, you should never compute the inverse of a matrix. You should just solve this linear system. What we have here is a linear system of equations. And once we do that, we have u star, and that's the end of the problem. Okay, that's the end. Now, perhaps this is too much of a trouble to solve the problem, and it's not so much about going into the trouble of writing down the equations, but somehow by eliminating the state sequence, we spoil a very nice structure that this problem has. And we end up having to solve this linear system over here, where this matrix is a dense one. This is a dense matrix. B transpose Q bar B plus R bar is dense, and that might be difficult from the computational point of view. There are other ways to solve the problem, and this is what we'll talk about next time, where we will talk about dynamic programming. So this is what comes next. And the KKT conditions of an optimization problem. So thank you very much for watching, and until next time, goodbye.